Let's start with handling missing data, a common issue in real-world datasets. We'll demonstrate how to identify missing values and then explore different strategies for dealing with them, such as dropping rows or columns with missing data, or filling missing values using various methods. This first section focuses on a fundamental challenge in data analysis: handling missing data. Real-world datasets are rarely perfect, and missing values can significantly impact your analysis and the performance of any models you build. We'll use the NumPy library, commonly aliased as NP, specifically for its np.nan representation of missing numerical values. We start by creating a sample Pandas data frame, missing_dfe, which deliberately includes np.nan in some cells across different columns. This allows us to simulate a typical scenario you might encounter with incomplete data. The first print statement in display missing_df will show you this initial state of the data frame so you can see where the missing values are located. Then missing_df.isNull.sum is a very useful command. It works by first applying the .isNull method to the data frame, which returns a Boolean data frame of the same shape, where true indicates a missing value and false indicates a non-missing value. We then apply .sum to this Boolean data frame. Since true is treated as 1 and false as 0 in a numerical context, summing down the columns, axis is equal to 0, which is the default for .sum, gives us a count of missing values for each column. This provides a quick and clear overview of how many missing entries are in each feature, helping you prioritize your cleaning efforts. Understanding the extent and location of missing data is the critical first step in deciding how to address it. Instead of removing data, another common strategy is to impute or fill the missing values. This involves replacing the np.nan entries with a calculated or predetermined value. The fill_na method in Pandas is used for this. The simplest approach is to fill all missing values with a constant, like 0, using missing_df.fillNA0. This is straightforward but might not be appropriate for all data types or analyses, as introducing zeros could distort the data's distribution. A more statistically informed approach for numerical data is to fill missing values with the mean of the respective column. We achieve this with missing_df.fill NA missing_df.mean. Here, missing_df.mean calculates the mean of each numerical column, and fill_NA then uses these calculated means to fill the np.nan values in the corresponding columns. This method helps preserve the central tendency of the data. Pandas' fill_NA is versatile and can also be used with other aggregation functions like median or mode, or even more sophisticated imputation techniques. We will display the data frame after filling with 0 and after filling with the mean to show the results of these imputation methods. The choice of filling strategy depends on the nature of your data and the potential impact on your analysis. Now let's look at handling duplicate data. Duplicate rows can skew your analysis, so it's important to identify and remove them. Pandas provides convenient methods to detect and drop duplicate rows based on all columns or a subset of columns. Moving on from missing data, another crucial step in data cleaning is handling duplicate entries. Duplicate rows in your dataset can lead to biased results in your analysis, especially in calculations of counts, sums, or averages. Pandas provides efficient ways to identify and remove these duplicates using the duplicated and drop_duplicates methods. We start by creating a sample data frame, duplicate_dfe, that intentionally includes identical rows to illustrate the concept. The first print statement and display duplicate_df will show you this initial data frame with the duplicates. The duplicate_df.duplicated method is powerful because it returns a Boolean series of the same length as the data frame's index. Each value in this series is true if the corresponding row is a duplicate of a previous row in the data frame, and false otherwise. By using this Boolean series to index the original data frame duplicate _df duplicate _or df.duplicated, we can easily display only the rows that are identified as duplicates. This helps you see exactly which rows are being flagged as duplicates before you decide to remove them. Understanding which rows are duplicates is essential before proceeding with their removal, as sometimes what appears to be a duplicate might be a valid, separate observation, depending on the context of your data. Once we've identified the duplicate rows, the next logical step is often to remove them. The drop_duplicates method in Pandas is designed precisely for this. When you call duplicate_df.drop_duplicates without any arguments, it removes rows that are completely identical across all columns, keeping only the first occurrence of each duplicate set. This is the most common use case for removing exact duplicates. We will display the data frame after applying drop_duplicates to show you the result of removing these redundant entries. However, sometimes you might only consider a row a duplicate if a specific subset of columns has identical values, while other columns might differ. In such cases, you can use the subset argument. For example, duplicate_df.drop. Underscore duplicate subset is equal to A and B will only consider rows as duplicates if the values in columns A and B are the same, and it will drop subsequent rows that match on this subset, keeping the first occurrence. We will also display the result of dropping duplicates based on a subset of columns to demonstrate this flexibility. The choice of whether to drop based on all columns or a subset depends entirely on your definition of a duplicate within your specific dataset and analysis goals. Data transformation is another key aspect of cleaning and preparing data for analysis. This can involve changing the data type of columns, applying functions to transform data, or creating new columns based on existing ones. Data transformation is a broad category encompassing various operations to change the structure, format, or values of your data to make it suitable for analysis or modeling. This third section explores some common transformation techniques using Pandas. We start with a sample data frame, transform_dfe, which contains columns with different data types, including a column B that is currently stored as strings object dtype in Pandas, but represents numerical values. The first print statement and display, transform_f, will show you this initial data frame and its data types using transform_df.info. Changing data types is a fundamental transformation. For instance, to perform mathematical operations on column B, it needs to be a numeric type. pd.to_numeric transform_df bracket B is the standard Pandas function to convert a series like a data frame column to a numeric data type. We then assign the result back to transform_df bracket B to update the column. The errors coerce argument, though not used in this specific example, it is good to know can be added to pd_numeric to turn any values that I cannot be converted to numbers into np.nan instead of raising an error, which is useful for handling messy data. We will display the data frame info again after this transformation to confirm that the data type of column B has been successfully changed. Understanding and correctly setting data types is crucial because many Pandas operations and functions expect specific data types to work correctly. Beyond changing data types, you often need to apply custom transformations to the values within a column. The .apply method in Pandas is incredibly versatile for this. It allows you to apply a function along an axis of a data frame rows or columns or to the elements of a series. In this example, we want to create a new column, A_squared, by squaring each value in column A. We achieve this with transform_dfa.apply applied lambda x such that x**2. Here we are applying a lambda function to each element x in the A column. The lambda function lambda x such that x**2 simply takes an input x and returns its square. Pandas efficiently applies this function to every value in the A series, and the results are collected into a new series that we then assign to the new column A_squared. The .apply method is very powerful because the function you apply can be any Python function, from simple mathematical operations like this example to more complex custom logic. This makes .apply a go-to tool for performing element-wise transformations on your data. We will display the data frame again to show the newly created A_squared column with the transformed values. Another common data transformation is creating new features or columns based on existing ones. This often involves combining or performing calculations on values from one or more columns. In this example, we will create a new column named D by simply adding the values from columns A and B. We do this with the straightforward operation transform underscore df bracket D equals transform underscore df bracket A plus transform underscore df bracket B. Pandas makes element-wise operations between series very easy. When you perform an operation like addition between two series of the same indexes and length, Pandas automatically aligns the operations based on the index, adding the first element of A to the first element of B, the second to the second, and so on. The result is a new series containing the sum for each row, which we then assign to the new column D. Creating new features from existing ones is a fundamental step in feature engineering, which is often necessary to provide your analysis or machine learning models with more informative variables. We will display the data frame one last time in this cell to show the newly added D column. This simple example demonstrates how easily you can create new features by leveraging basic arithmetic operations on Pandas series. Handling categorical data is also a common transformation step. Categorical data can be nominal or ordinal. We often need to convert categorical data into a numerical format for analysis or modeling. One common technique is one-hot encoding. Handling categorical data is also a common transformation step. Categorical data represents values that belong to a limited set of discrete categories. Categorical data can be nominal, where there's no inherent order, or ordinal, where there is a meaningful order. While some analyses can work directly with the categorical data, many statistical models and machine learning algorithms require numerical input. Therefore, transforming categorical data into a numerical format is a frequent and important step. We start with a sample data frame, categorical underscore df, containing a single column category with a few distinct categories. The first print statement in display, categorical underscore df, will show this initial data frame. One of the most common techniques for converting nominal categorical data into a numerical format is called one-hot encoding. This method creates new binary 0 or 1 columns for each unique category in the original column. For a given row, the column corresponding to its category will have a value of 1, and all other category columns will have a value of 0. This prevents the algorithm from assuming any ordinal relationship between categories where none exists. The pd.get_dummies function in Pandas is the go-to tool for performing one-hot encoding. When you apply pd.get_dummies categorical underscore df bracket category to a series, Pandas automatically identifies the unique values in that series and creates a new data frame. This new data frame will have columns named after each unique category. The values in these new columns will be 1 for the category present in the original row and 0 for all other categories. The prefix is equal to category argument is optional but highly recommended. It adds a prefix to the newly created column names, which makes the column names more informative and helps prevent naming conflicts if you perform one-hot encoding on multiple categorical columns. We will display the data frame produced by pd.get_dummies to show you the result of the one-hot encoding process. Notice how each row now has a 1 in the column corresponding to its original category and 0 in the others. This binary representation is suitable for many downstream analytical tasks, including machine learning model training. After generating the one-hot encoded columns, you typically want to integrate them back into your original data frame. The pd.concat function is used to concatenate or join Pandas objects along a particular axis. In this case, we want to add the new one-hot encoded columns as new columns to our original categorical underscore df. The first argument to pd.concat is a list of the Pandas objects you want to concatenate. In our case, the original categorical underscore df and the newly created df underscore 1 underscore hot underscore encoded. The axis y1 argument is crucial. It tells Pandas to concatenate the objects along the columns. Axis 1. If you used axis 0, the default, it would try to stack the data frames vertically, which is not what we want here. The result of the concatenation is a new data frame that includes both the original category column and the new one-hot encoded columns. We then assign this back to categorical underscore df to update the data frame. We will display the final data frame to show how the original categorical column is now accompanied by its one-hot encoded representation. This combined data frame is now ready for analyses or models that require numerical inputs for categorical features. Remember that you might choose to drop the original categorical column after one hot encoding if it's no longer needed.